Okay, so within this learning objective, we're going to learn how to utilize what we learned in the previous one, which was to write the reactions for these insoluble salts and write the equilibrium constant expression for the salts. We're going to be able to use that and convert between what's called molar solubility and the solubility product that we learned about there. And we're going to learn how to rank salts according to their solubility, which one's more soluble, which one's less soluble, by looking at either molar solubility or KSP. So as you look at these boxes down below in this slide here, we see that we can convert between what's called KSP and molar solubility. So the KSP is one way to express how soluble salt is, and in general, the smaller the KSP, the less soluble the salt. Now that comparison really only works well when you're comparing salts that have the same general formula. So you might compare a salt with a formula like Mx to My. They have a 1-to-1 ratio, but it might not be good for comparing Mx to another substance of Mx2, where there's 2 anions for every 1 cation. So you have to be a little careful when you're comparing KSPs for these insoluble salts and say who's more soluble, who's less soluble. But the other way of expressing solubility is what's called molar solubility, and here's the definition. It's abbreviated with a lowercase s, and it's the number of moles of solute in 1 liter of saturated solution. It's in units of moles per liter, in other words. It's molarity, and it's basically the molarity of the amount of the salt that dissolved. So if you're given one of these two, either the KSP or the molar solubility, you can calculate the other by way of determining the concentration of the ions in solution. In our first example problem, we are given the KSP of this lead chloride and we're asked to determine the molar solubility. So is that with any equilibrium problem, you want to start with a reaction. We're not giving you the reaction. We expect you to know the reaction. You put the solid on the left. You put the ions on the right. And I will leave room for an ICE table. And I'm going to write the KSP expression. We have the lead. We have the chloride. And it's squared. So what's happening here? We have a beaker of water. And we're going to dump into that water some lead chloride. Lead chloride is not very soluble, so most of the lead chloride will sit at the bottom. We are going to dump an excess of lead chloride in there. And some people do that. They just say excess, but that looks too much to me like x minus 5, and writing out excess I just don't do. So what I generally write is I put some of the lead chloride into solution. I put a bunch. And I will put 0 because none of it's dissolved yet. I will allow, instead of using x's, I'm going to use s's in this change line because s, and I always use a script s because my s looks too much like a 5, is molar solubility. And where I have written molar solubility, this S here, that's how much lead chloride dissolves. So by definition, that S, or what sits right here in my change line, by definition is molar solubility. And so that's why in any textbook you look at, they use S's here. But we'll follow that S change across to the product side, and we'll S and 2S. And only a little bit of that lead chloride dissolves, so there's still some in the E line, but we'll have S and we'll have 2S. So we'll come to our expression and plug in what we know. We know the KSP that was given to us, 2.4 times 10 to the minus 4. For lead, there was an S, so we'll put an S here. For chloride, there was a 2S, so we'll put a 2S here and square it. That will give me 2.4 times 10 to the minus 4 is equal to 4. You see where the 4 came from? The 2 squared. And then S cubed. You see why it's cubed? You've squared this S and you multiplied by another S. So now we can divide by 4 on both sides and give me an S cubed equal to 6.0 times 10 to the minus 4. Then we can take the cube root of both sides, and that will give me S equal to 3.9 times 10 to the minus 2. Now it has a unit. It's how much dissolved in moles per liter, so it's in molarity, and that is the value for the molar solubility of lead chloride. Okay, so in this problem we have molar solubility given to us, and we're trying to determine KSP, so it's the reverse of the previous problem. But we begin by writing the reaction, same as we did before. We have the solid on the left, the ions it breaks apart into on the right. I will do an ICE table, but before I do that, I want to write my KSP expression. Manganese 2 plus, carbonate. So far, nothing's different. We are going to dump some of the solid into our water. Before anything happens, we don't have any of those ions present. Now here's where it varies. We could put minus S here, but we know what the solubility is. Remember, S stands for the molar solubility, and that was given to me. So I know how much of this is dissolving. Not very much, but some is dissolving, that quantity. We carry the change line across, so we are going to produce 4.2 times 10 to the minus 6 of this substance, and produce 4.2 times 10 to the minus 6 of the carbonate. So there's a large excess of the solid, so there's still some sitting on the bottom, but we now know the quantity at equilibrium of these two substances. So KSP's value would simply be 4.2 times 10 to the minus 6, which is the manganese's concentration, times 4.2 times 10 to the minus 6, which is the carbonate's concentration. When I multiply those two values, I will get 1.8 times 10 to the minus 11. And that's the KSP of manganese 2 carbonate. Okay, we're going to work this one together, but before we work it together, I want you to figure out the molar solubility of this salt. So let's describe what's happening here. You were given the solubility not in moles per liter, but in grams per liter. We can't use the KSP expression unless we know things in molarity, so your job is to take this information and determine which one of those answers is the molar solubility of this compound. Well, did you choose B? If so, that is the correct answer to 2 decimal places, or 2 significant figures. Now we're going to complete this problem together. Oh, there it is. Green check mark. So now we have space to work the problem, and we're going to start by writing the reaction. The solid is Mn, or M2X3, and it's turning into the ions in aqueous solution. There are 2 of the metal ion. It probably has a 3 plus charge. And 3 of the anion, it probably has a 2 minus charge. Its charge is not important, but that's probably the charges if they are. I'll leave room for an ICE table, and I'll write the expression, the KSP expression down here. KSP is the metal ions concentration squared times the X concentration cubed. Okay, so we'll fill in our table. We have some solid that we put into the beaker. There is none of the ions to begin with. We figured out with your previous question that you answered what the molar solubility of this salt is. I'm carrying a little bit extra sig fig here just to carry extra until the end. It was actually 1.25 just to carry the extra. This is the molar solubility. We carry the change line across, so it's got to be twice 1.25 times 10 to the minus 19 here, and 3 times 1.25 times 10 to the minus 19 here. So there's still going to be some of the solid on the bottom of my flask. But now we're going to have 2.5 times 10 to the minus 19 and 3.75 times 10 to the minus 19. Now we're ready to obtain the KSP value. For the metal, we put 2.5 times 10 to the minus 19, and that is squared. For the non-metal, we put 3.75 times 10 to the minus 19, and that is cubed. When you plug these into your calculator and obtain a value, you will get 3.3 times 10 to the minus 93. So that's an absurdly small KSP value for this hypothetical ionic compound. But I wanted to show you that these coefficients come into play twice. They come into play in the change line, and they come into place in a power. So that's the end of this learning objective, where we have learned to convert between a KSP value and molar solubility.